So friends, I am going to derive an expression for air standard efficiency of the Otto cycle. In the earlier class, we talked about the assumptions which are made in the analysis which is known as the air standard cycle analysis. So with those assumptions, I am going to analyze the Otto cycle. By analysis, I mean I will be calculating first the air standard efficiency of the Otto cycle. Now Otto cycle, is the thermodynamic cycle for a heat engine, and it closely resembles the petrol engine. So heat engine, if you consider any heat engine schematic is like this. This is suppose the heat engine. So heat engine, you supply certain heat and the heat is rejected partially and the remaining heat is converted to work. It means that the work of the heat engine is equal to heat supplied minus heat rejected, and the efficiency of the heat engine is the work upon heat supplied. Okay, so efficiency of the heat engine is work upon heat supplied, and work is heat supplied minus heat rejected upon heat supplied. Now in the Otto cycle, we had seen that the heat is supplied. This is a pressure volume diagram of the Otto cycle, and this is the temperature entropy diagram of the Otto cycle. So we know that heat is supplied during this process 2 to 3. This is the process 2 to 3 where heat is supplied. Heat is supplied, and this is supplied at constant volume. So heat supplied would be mass into CV, where CV is the specific heat at constant volume, minus the change in temperature. You see that because of heat supplied, the temperature increases from T2 to T3. So the temperature difference is T3 minus T2. This is the heat supplied. Similarly, the heat is rejected in the process 4 to 1. Heat is rejected in the process 4 to 1. This also happens at a constant volume. So the heat rejected QR is equal to MCV T4 minus T1. T4 minus T1. This is the heat rejected. So if I put this values over here, so this is QS minus QR means 1 minus QR upon QS, and this QR is 1 minus MCV T4 minus T1, and this QS is MCV T3 minus T2. You see over here that CV cancels off, M cancels off, and you are left with this expression. So the efficiency becomes this. What it becomes? This becomes the efficiency. So this is the expression for air standard efficiency. Air standard efficiency in terms of temperature for the Otto cycle. Now I want this expression in terms of compression ratio. Now what is compression ratio? Compression ratio for an engine is equal to the total volume upon the clearance volume. Now you know that the piston moves from V1 when it is at TDC, and when it is at TDC, the total volume is V1. It is V1 and the clearance volume is V2. And you also know that V1 is equal to V4. So that is also equal to V4, and V2 is also equal to V3. So this is the formula for compression ratio. Compression ratio is V1 by V2 for a Otto cycle, or it is also equal to V4 by V3 for a Otto cycle. So let me now derive an expression in terms of compression ratio. So what I do is that I would express this T3 as a function of compression ratio. I will express T2 as a function of compression ratio, and then finally I would get the expression in terms of compression ratio. So how will I do that? So for that, I consider the process T2 1 to 2. So 1 to 2 is what? 1 to 2 is T2 by T1 is equal to V1 by V2. But what is V1 by V2? V1 is the total volume, V2 is the clearance volume raised to gamma minus 1. Okay. So this is Vt upon Vc is compression ratio R upon gamma minus 1, where gamma is the adiabatic index. So T2 is equal to T1 into R raised to gamma minus 1. Okay. Now how do you get this expression? This expression you can derive. This is left as homework. I am not deriving this. Just by substituting this P1 V1 raised to gamma is equal to P2 V2 raised to gamma, and P1 V1 by T1 is equal to P2 V2 by T2. If you solve this to simultaneous equation, you will get this. Okay. But no need of deriving this. Straight away you can write T2 by T1 is equal to V1 by V2 raised to gamma minus 1. So T2 is equal to T1 into R raised to gamma minus 1. This is for the process 1 to 2, which is reversible adiabatic or isentropic. Reversible adiabatic or isentropic compression. Similarly, 3 to 4 is reversible adiabatic or isentropic process, and for that also we can write T3 by T4 is equal to V4 by V3. Now V4 is what? V4, as I had written already here, V4 is V1 and V3 is V2 and it is equal to R. So this becomes R, this is V1, V4 is V1 and V3 is V2. So this is same thing as this earlier thing. So this is R raised to gamma minus 1. So T3 becomes T4 into R raised to gamma minus 1. So what I have done is that I have written T2 as a function of T1 and R, and I have written T3 as a function of T4 and R. Okay, so T2 and T3 I have written. T2 and T3 I have written as a function of R. Okay, now just let me substitute this in the earlier equation. So what is T2 I had got? I had got T2 as T1 into R raised to gamma minus 1 and T3 as T4 R raised to gamma minus 1. So this becomes T4 minus T1 upon T4 into R raised to gamma minus 1 minus T1 into R raised to gamma minus 1. So this is, if you take R raised to gamma minus 1 outside, so this is T4 minus T1 upon T4 minus T1. And you see that this cancels off, and what you will be left is, you will be left with this efficiency would be 1 minus 1 upon R raised to gamma minus 1. Why is that happening? Because you are left with this numerator, which is T4 minus T1 and T4 minus T1. T4 minus T1 and T4 minus T1, they cancels off, and this is the efficiency of the Otto cycle in terms of compression ratio. Okay, so this is how we need to derive the expression for efficiency of the Otto cycle. Okay, so this is a very important derivation. Okay, and very simple one. Thank you.